Start. So this session is Lambda expressions. I was mentioning earlier, it's a lot easier to talk about Spirit or the asynchronous I/O library because those are libraries that I use all the time. Lambda expressions, I'm feeling even more intimidated because there are people inside this room who worked on them in the language committee. So there might be issues along the way. I was going to retitle it after Tony's session. I was going to title it How I Use Lambda Expressions. And I thought I might get away with that. So if somebody mentions something, I'd say, well, this is how I use them. But I have a set of standard disclaimers. And these have come about over time because I usually get critiqued at some point about my slides. It's hard to make slides where you're trying to demonstrate something and also have good code in the sense of you're doing things stylistically the way that you want to see them. And so you're not going to see a lot of namespace unless it needs to really happen in order to get an idea of something like function, for example. Many of us probably use boost function. You know, when I'm using standard function, we'll make sure it's a standard. So something like that. All right, let's go ahead and get started here. This snippet of code came out of something I was working on at a client's code base 2 weeks ago. And how many, when you see this, immediately want to do something about it? Okay, about half of you. Yeah, so it kind of rubs you funny because we're doing these while loops of some sort or another and looking at iterators. And you know, the first thing you probably want to do is something like a for each. And so you start writing your for each, and then you realize that you're going to need to somehow create a function for your for each to work upon. And here we're going to go ahead and use a functor. And now I have a problem where my functor is going to be somewhere else. But I'm somewhat happy with it. It's somewhat generic. This is the type of thing that we could argue about on the Boost mail list for hours and hours, whether or not B and T should be of the same types in order to go ahead and get the product of them. And somebody would eventually get beaten down and you change it. But this might be your first step, but then you would write this and you say, boy, I really don't like the fact that the functor is somewhere else, and now I'm not sure what's going on. This is going to be easy. It's got a nice name product. So I personally love Boost Phoenix. So this is what I would do. I would go ahead and just insert something with Phoenix. I still have some of the same advantages. It's polymorphic. I don't know what this thing is, and I don't care. It's going to take care of it when it goes ahead and creates the function objects for me. And now everything is nice and compact, and it's in one spot. But that has problems too, right? Phoenix is a library. It's compile time hits. Some places won't let you use it. And most importantly, this is a C++11 talk, and so we're not going to be using Phoenix. We're going to go ahead and use Lambda expressions. All right, and so we have a Lambda expression. Probably by this point you've seen several of them already today. All right, let's move on. We've got then our before, and we have our after. And while, as we go throughout this talk, we're going to find out some other ways that we might want to change our after. It's considerably improved. We have something where, I don't know, I'm going to have to take some time and think about what's going on versus something that it's right in front of me. It's taking up 3 lines, it's all in the visual part, and I just know what it's going to do. So let's go ahead and compare just for a moment the concept of functors and the Lambda expression that we have. So here at the top, we have this struct called mod. It has a function called operator that takes an int and returns an int. And it goes ahead and takes whatever it's given as its parameter and does a modulus division. We want to keep some state in this thing, and so we store the modulus by passing that in within the constructor. And so this is easy enough to use. We can do a transform, passing it in the begins and the ends, and we have where we want to put the output, and we can go ahead and construct our functor here, providing the state of what we want. So that's pretty nice. Let's take a look now what we've got going on. The lower section, we have the lambda function, or the lambda expression. The lambda expression also has very similar bits and pieces. Up here, if you remember, we're going to have, and capturing state within the constructor, we're storing that state within the struct. Down below, we also somehow are capturing some state. We're utilizing that state then inside of our lambda statement. We have parameters up here inside of our functor, the parameter v, and also within inside of our lambda expression, we also have a parameter. And each of them return something. The function call operator returns an int, and right here we're returning an int within our lambda function. So there's a lot of similarities between the two, and that's not by mistake. So let's take a look, dive in a little bit further at the different parts that make up the lambda expression. I often wonder if they sit around thinking about really cool names that they can name things like you do in a company, and then you don't ever show anybody those names later, and you have to come up with generic ones. So it's like introducer is what makes it inside of the standard, but I always wonder, what was the name before that somebody typed it down or went in there to change and replace whatever the cool name was. So lambda expressions begin with open and closed brackets. That is how we introduce that we're going to have a lambda expression. Within the lambda expressions introducer, within the square brackets, we're going to have our capture. We have parameters. We have a return type, and then our statement. So these are the main parts. We're going to go through each of these. Between the introducer and the statement, whatever ends up there is the declarator. And it could be a lot of different things, but as we're going to find out here in a moment, it's optional. And so you now know its name. We're going to use it later. The lambda expression, when it's evaluated, will become a closure object. So we're going to evaluate this expression. And when the expression is done being evaluated, there's going to be an unnamed object. It's called a closure object. And the closure object behaves just like a function object. So we can think of it as a function object in every other way that we normally would. All right, very simple lambda expression. This expression has our introducer. It becomes a closure object. And now what do we do? So now we have a closure object. And I don't know how many of you were like me when you were starting off, but it just drove me nuts when people did stuff like this. So I had to put it on the slide. This is going to create the closure object, and then we're going to go ahead and call the closure object, just as if we would a functor. And I might be slow, that might be what it is, but I remember the first few examples, not of lambdas, but many years ago, things like this that I saw, and I'm kind of like, I don't know what they're doing. This looks really, really odd. And finally I realized, right? So we just call it like anything else, right? Like any other functor. We go ahead and make that call. And then we get, ooh, outside. We can pass parameters. And we can do things with inside of our statement as we would expect. So here we're now passing in our 7. And of course we get 42 because that's important. We can pass parameters by reference. And then we can do exactly what you would expect, the parameter being passed by reference. Multiply equals 6. Passing in our I. Going to print out I. And of course, again, we get 42 because that is the right answer. We can pass them in by const reference if we want. And it will do exactly what we would expect, not work. So we get assignment of read-only reference. I'm excited, by the way, whoever was mentioning earlier that Clang will be supporting lambdas in this next major release. Is that all right? Because I normally like to use Clang for my slide outputs because they have nice messages and stuff. So we're going to be looking at GCC output. But how many of you here have used either Boost Lambda or Phoenix? Good number of you. If only it would say something like this. I'd be so happy, right? So after scrolling pages and pages and pages and pages and pages, you then get on IRC and you ask somebody, how come this didn't work, right? And so there are a few people in the world who are really good at reading that output and they can tell you immediately why it didn't work. But here, this is great, right? We now have lambdas as a built-in thing, and the compiler can tell us exactly what's wrong. Assignment of read-only reference V. I mean, it couldn't be clearer, right? This is wonderful. Okay. So here, we're passing in J, and within it, we're going to go ahead and V will then be a local variable within inside the statement. We're going to go ahead and multiply equals, and then we're going to print out within it, and again do the same thing. The point of this, and I like to learn things by doing and seeing, and these slides basically follow my natural. I wonder if this works. I wonder if this works. So after reading the standard, pages 5, 1, 2, is that right? 5, 1, 2, a million times, and at some point you want to just, I wonder if this works. And so, do these things just work like you would expect them to work, like normal local variables? Well, sure enough, they do. All right, so we're going to go ahead and create a local variables J, name J, value 7. Our lambda starts off. It's going to take two parameters, an int by reference called B, and an int named J. Multiply equals. Here we're going to pass in J and 6. And indeed, we're going to get exactly what we want and expect to get, because J is not going to affect the namespace of, what's the right word, the closest namespace. The scope. Thank you, the scope. So our variables within our parameters aren't affecting our scope. All right, these two are the same. So parameters are optional. You don't actually have to put it in there. And with the possibility of saying this, and then with knowing that there are people in the room who work on this stuff, and then getting all kinds of hard questions later, in human interface designs, if there are lots of ways to do things, we pick one so that it makes it easier. And typing like open, closed, parent all the time, it would have been easier to teach this language to someone else later. They're optional, but you'll get used to it. Be there or not be there. All right, pretty commonly want to capture state, as we had seen previously. And so in our functor that we had previously, we had this, where we have a constructor. We're going to capture our state as we create it, and then we can work upon that as it actually gets executed. Here, we're going to go ahead and have our capture with inside of the introducer. So it's an optional capture, and there's all kinds of different ways that we can use it. We can capture all by reference. We can capture, which is this, we can capture all by value. We can go ahead and list a set of identifiers. And we can do that either by value, or we can do that by reference. We can do combinations of those. We can say we want to capture all by reference, except for these particular identifiers we want to capture by value. And then the opposite, we want to capture all default by value, except for these particular ones we want to capture by reference. Let's take a look at a couple of these. So previously, we had total elements in here. Instead, this time, we actually have capture all by reference. And so within this scope, and we'll talk about what that means in a little bit, we're going to capture total elements as if we had listed it inside of our actual capture. So this is going to capture total elements by reference, and we can go ahead and do our multiply equals, and we'll do exactly what we expect. Take a look at something a little more complicated. All right, I've got this method called fill, and it's going to take a vector events by reference and something called done. While we're not done, we're going to go ahead and push back the next value of I and then increment. So down here, we created our vector. It's called stuff. It's a great name. And we're going to call fill with stuff and then a lambda expression. And this lambda expression is capturing default by reference. And it's returning stuff, the size of stuff, greater than or equal to 8. So if all goes well, within our fill, every time we go ahead and check whether or not we're done, we're going to go ahead and execute is stuff size greater than or equal to 8. And sure enough, it does. Yes?
I could be misremembering this, but to leave off the return type of a lambda, can you also leave off the return keyword with that?
I don't believe so.
No?
No.
Return is always required?
Return is required.
Okay.
Yeah, the section says that we'll actually get to the word in a few more slides. Any other questions? Yes.
I have a question related to the T done.
Yes.
Whether that should be a reference or not.
Great question. So it's not a reference. So what am I doing?
By value.
Yeah, by value. So I'm making a copy, and a little bit later we'll talk about copies and what we actually get for free or is given to us out of our Lambda. So our closure objects have some certain functions that happen to be there. One of them, clearly, we can make copies. Why? So let's answer the question, why don't I have to pass it by reference?
Because the information about the code for that function is part of its type.
Okay. Not only is it part of its type, but it's part of its type and the information is by reference. So we're going to copy a reference to stuff when we go ahead and pass in our closure object. So indeed, we're going to pass our closure object by value. We're going to get a copy, but the copy contains a reference to stuff. Obviously, if our reference to stuff goes away, we're in trouble, right? Stuff goes out of scope, and we still have this lambda floating around with a reference to something that is out of scope, then it's undefined. Right, same idea, but let's do something a little more interesting this time. All right, again, we're going to capture by reference. And within here, we're going to go ahead and create a local variable called sum, initialize it to 0. And we're going to go ahead and have a for each. stuff. So we're going to iterate across stuff, and we're going to go ahead and add them all up. This capture is also by reference, and it's capturing sum. At the end, I'm going to check whether my sum is greater than or equal to 10. With any luck, every time this runs, it will go ahead and add up what we've got so far inside of our vector. And as soon as we're done, meaning that the sum of the elements within the vector are greater than or equal to 10, then we're done and we'll exit out. Go. And we get 0, 1, 2, 3, and 4.
Does it capture stuff as well, though? The inner lambda?
The inner lambda is not capturing stuff, and we'll talk about why. But in essence, we might talk about it now. The inner lambda is not using stuff. So there's no need to capture it.
But if it were, it would have.
If it were, it would capture it, and we'll talk in a little bit about how it captures it and the different variations of that capture. Yes?
Since you're using for each there, if I capture this return value, would that be my lambda again?
The return value of for each?
Yes.
Okay, so I'm stumped. What is the return value of for each?
I think it returns your.
It's the functor. It returns you the functor, so you can take that out of
Oh,
it.
is it? That makes sense.
And that leads to my next.
That's a
little
slide
question.
coming up later also on something else, but
Well, then I'm wondering, you're bringing some in from outside, but could I do something evil like inside lambda and say static sum is your
static int sum.
That is have the int.
Oh, within your lambda?
Yeah, on the lambda, because it's for each, I know I'm calling it once and I get it back again, and thus I can get my state out, because I'll do that with functors, for example. Could I do that with lambda?
I don't believe you can. But now I'm going to look around the room because all the smart people in the room still, right? No, I don't believe you can do that. All right, any other questions on where we are so far?
Could you ask about static? If the lambda is technically equal to any other function, it should behave just like a function.
You're correct. And so now I have homework, and I got to go find out.
Yeah, it doesn't have a name, so it's
But
totally anonymous.
you get the return object back from the for each. If I was real daring, we type it in. But we're not going to.
I think the question is, can you then access a variable in that? It would surprise me if you could.
If you could.
Yeah.
Yeah, because its definition isn't visible.
I don't know how you could.
Well, you could return it.
No, you're returning a closure object, which has, which we haven't talked about all that it has yet, but
No, inside lambda you can return, because if you're just accumulating state inside lambda, you don't care about its return type from point to point. You just care about it at the very end. So you can just call the lambda and get the sum output.
So each time before we
Yeah.
just calling it, we're ignoring the return
Right.
value.
I don't know. This seems reasonable.
So we find out that way.
Let's take it.
Are you going to talk about, anybody have any other hard questions at this moment? 'Cause we're just going to roll them now. All right. Let's go ahead and talk about capture default all by value instead. So we just looked at, we can capture by reference, now we can capture by value. So here we're capturing my mod by value. Where's the value actually captured at? So at what point do we capture V? In this example, we're assigning V to 42. We're using auto. We're creating, our lambda expression will be evaluated. It'll create our closure object, which is then being assigned to func. Then we're setting V to 8, and then we're going ahead and calling func. So what are we going to get? What do you do? Love the smart crowds. Yeah, so obviously, if we're capturing by value, it's going to be captured at time of the evaluation. If we were wanting 8, if that's the behavior we wanted, then what would we do instead? All right. So here we're capturing by value. We're getting fancy now. We have no parameters. We're leaving them off. We're taking I and multiplying equal 2, and we're returning I. And it does this amazing thing. It comes back and it says that I is in a read-only object, and I am trying to assign it something. What's going on, right? So closure objects have an inline function call operator that has a signature, the parameters that match the expression, the lambda expression, and the return type that matches the lambda expression, and it's const. And so we can't just go around doing this, which is really the behavior you want most of the time. When you capture something by value, you kind of want it to be that value. But if you insist that it's not, you can go ahead and use mutable. Now we do whatever we want. So we've captured I. We're returning I. So at this point, we'll go ahead and print out 2I, which is 20, but I, of course, is still 10 because we've captured by value. Question? Yes?
Are the open parentheses required if you use mutable?
Yes.
Okay. If you have the return type, does that come before or after mutable?
The return type comes after the parent.
Okay.
Is that fixed? Anybody know? Is it required to be after the parent? I don't normally have to do this in other sessions when I, do training. It's like they just believe me. I say it with confidence. Return type always comes after parents.
Yes.
It's after mutable?
Yeah.
Thank you. There you go. Now you know.
Hey, Michael?
Yes.
Is there, if you were a psycho,
Yes.
you wanted to write out the auto, I assume there is a syntax under which you could write out the auto?
I don't believe so.
Yeah.
Now somebody could correct me on that, but I was unable to find it because that was my intent, was to write it and then show auto's really cool, right?
Right.
I just
Yeah.
I believe it's function, left bracket, void, left paren, void. I've written.
That's not,
cast.
but that's not the same.
Really? Because it'll capture that.
But that's different.
Okay.
I mean, the question
I did not know
is,
that.
and so let me, if I can remember exactly what the standard says, I won't get an exact quote, but every closure object is a unique type. So I don't know where's STL, but I don't know, you can probably tell me exactly what that means. But I mean, I think every closure object, or Howard, right? I mean, my assumption is if I have this lambda expression, exactly the same lambda expression, twice, they're going to have 2 different unique types. So I don't know what they are.
It means they get mangled to 2 different names.
Yeah.
But they could be held by the function that you described.
Right.
The function.
We'll get to that later. You guys are just so smart. You're trying to move ahead constantly. Yeah, I'm not clicking fast enough. That's it. All right. GORP. I tried hard to get slushies into this presentation and slushie holders and things like that. And this almost made it, but not quite. But let me just tell you what the intent here is. We have this thing called GORP. And it's going to get initialized with some modulus. And it has this put, where I can go ahead and put lots of information, like I just got 13s of something and 12s of something. And At the end, I want to go ahead and calculate what the extras are. So how many didn't fit in the crate, or how many didn't fit in the slushy holder? And I got to keep them within lots. So there'll be extras out of each lot, and they can't get mixed together again. What? So here we're capturing by value, default, all by value, but count we're capturing by reference. GORP within it has this vector of ints called values. It has m underscore, which is the modulus value. As we go ahead and call put, we simply push back the new values. And extras then uses a for each, taking, of course, the value that's inside of the vector, doing the modulus division of that value and whatever we had captured, and then adding them all up, and then we're going to return the value. So we create one of these with a modulus of 4, and we put in 3 and 7 and 8, right? And if everything works out right, we should get 6. All right, so value, count is being captured by reference. Count's easy. We go ahead and we've initialized it to 0. We're going to use that to accumulate our result and return it. But what's with m underscore? How in the world did we get m underscore?
We captured this by value.
The guy in the front row. We captured this by value. And so we have an implicit capture of this because we're using m underscore. And so now we can go ahead and treat anything that happened to be there as if it was within this local scope without using this. So m underscore is this.
So let me ask you, in that case, in the context of that class,
Yes.
is equivalent to say equal, I mean capture everything by value, than saying this?
Is it equivalent to say
Equal or this?
you can, we will get to the rules of what you can mix and match. You cannot have equals and this.
No, I wasn't meaning that. I wasn't meaning instead of putting equal, if
Yes.
I change it.
Yes, you could have this, and then you could have count.
In that case, would have been the same effect in the context of the class, because the lambda is being defined in the context of the class GORP, right?
Yes.
So would have been interchangeable in
It would have
this
been
context.
identical.
Okay.
But you said implicit this capture, then you don't need an equal. Right?
That I was trying to.
He's trying to make a new example.
I have a different question.
Oh,
And that question is, if you get this by implicitly, did you truly need the equal?
yes, you need the equal to capture by value, by the default by value. M is what you're using, but M is not in our local scope. M comes about via this, and so the wording is that this is implicitly captured.
If you remove the equal, then all you're capturing is count.
Yeah, if we remove the equal, we're only capturing count. Absolutely.
You get a compile error on M.
And you would get a compiler error on M. And it's really cool because it's only like one line instead of pages and pages of compiler error. Yeah. I'm really liking that.
I was going to ask about this, but now it seems like since you're using m underscore there, it's just finding out that it must be the member of this that gets copied passed by value. So I was going to ask whether values is going to be copied as well, since you're passing this by value, but apparently not. So it's just the name resolution there. So we don't make an extra copy of values when
You
we
should
capture
know. You should
this by
not.
value.
Right, you capture what you use.
Yes.
And so what we're actually using is this. And we're going to see that in a moment. At least in an example that totally surprised me. It caused me to reread the standard probably 3 or 4 more times until I finally figured it out. So,
But then, since you captured this by value, it's only const, right? Unless you say mutable, so you can change. And
we'll come back to your question.
If you would capture values by value and not use it? Do you know if it would actually make a copy?
I do know, and you'll find out in like 3 more slides. I had the same question. Unless I can answer that for GCC. I mean, I don't know. All right, so the question is now, will this compile? I have a struct foo. It has a parameter I that's initialized to 0. This incredibly amazing method that does nothing except for setting I equal to 8.
Last line of failed to compile. I'm sorry, it's a struct. I guess I better have another cup of coffee.
You're good.
Thought I had.
Does anybody else have another opinion of whether it will or won't for a reason?
It should fail to compile because I is constant, because the lambda is not representable.
Okay, so that was my answer also, but this was the result.
It's only this is constant.
Right, so this is const. And this sent me through tailspins for hours. Because to me, this is not obvious behavioral. It was after I thought about it long enough, but this is being captured by value. It is constant. You're not changing this though, are you? Okay. Yeah. So, yeah, f dot I is actually 8. Does that make sense to everybody? Or does it maybe not make sense?
If we're dealing with a constant method of foo, it would not be able to assign I, because although I is not declared constant, we inherit its constants from the constant is. Okay, I'm not talking about lambdas now.
Okay. No. Yes.
We just have structure
Right.
S into I.
Right.
Now we declare a constant method on foo.
Right.
The constant method is passed a const foo star implicitly as this. Because of that, we can't assign to I, because the I picks up constants from the const this.
That is actually true.
Why isn't that happening in this case?
The difference is between a pointer to const and a const pointer.
So, yeah.
And finally, a const pointer to const.
Right. So just read them backwards, right? So a const pointer, the pointer cannot be changed. You know, this used to be my classic interview question until somebody leaked it out. Yeah. What's the difference between const char star or char const star and char const star const? You know, and then all the other combinations. And everybody does. So I'm hiring in a bad area, that's why. But yeah, the pointer itself is const, but not the thing it points to. That's the thing to keep in mind. Yeah, so this did send me through a tailspin for that.
So obviously, if you make amazing constant method, this will fail to compile.
If you make amazing a const method,
That's compiled. It will fail to.
Because it would have to modify the state of
This
that is not true. It will still compile.
What he's saying is that
Oh, it shouldn't
amazing
compile.
has captured the distance passed. If amazing were a constant method, it would be passed a pointer to constant foo.
So,
It comes pointer to constant.
Yes, yes.
right, const pointer.
Which is why you probably don't compile.
But yeah, somebody typing this in. I said to bring your lambda enabled compiler. This would be a good one.
I typed it in plain, plain doesn't like it, to be honest.
Plain does not. Do you have GCC too, by the way? Just wondering.
No, I don't.
Okay, the only reason I asked is because I think I actually tried that last night because it knew some weird apps.
Yeah, I won't claim to say that Clang is right here. I do not know. This is too confusing.
I will claim that Clang is right here.
Good answer.
I trust,
So-
on this issue, I trust Doug. And
Yeah.
I think he would have been very, very particular.
I'm fairly, so that's what I expected, because I actually tried to make a slide last night to help clarify some of this. And sadly, I'm in Windows because the USB to RGB thing only works there. But as soon as I reboot into Linux, I'll look and see whether it's compiled or not. All this code, I can give you guys the code that's in all the slides too. Learn not to present without compiling in front of the boost crowd. All right, so I have another outstanding question. The list is getting longer. This is actually why I'm videotaping, so I can write my questions on there. There are restrictions to the capture, though. And we mentioned a couple of them actually already. So first of all, identifiers can only be listed once. And of course, you'd say, duh, who would not? But I can tell you, one of the clients that I'm working for, we're doing some, we think they're neat tricks. And they're generated code via some macros to make an interface that was very ugly, easy to use. And the actual solution was a bunch of lambdas that get generated and passed in as parameters, and ended up not being so easy to make sure that certain things were true. So identifiers can only be listed as once. This is bad. These listed twice. Default by value. Explicit identifiers then have to be by reference. You can't capture default by value and then list by value. So the equals and the this, they don't go together. And then here we have the same type of problem. Does that make sense? And then the opposite. If you capture default by reference, then you must capture by value if you explicitly list an identifier in the identifier list.
What happens in the second case if you don't capture this explicitly?
This is not captured by reference. Was that the question?
Yeah.
Yeah, so this is captured either by value or explicitly listed in the capture list.
Okay.
So I'm a little confused. What exactly, when you say capture this, is it capturing the this pointer
By value.
by value? So you're capturing everything by reference and one thing. Ah, yeah, okay, got it. Thanks. Yeah.
Which is sort of the default is value.
Yeah.
You don't just
Right.
But you don't specify the constants anyway.
Not in capture.
And like everything,
You know, I thought
this makes sense, and then you.
an hour and a half for Lambda. I had first set of slides I wrote had a lot of interaction. There's less of that.
GCC 4.7 says that foo I is read-only when the actual amazing is const.
Thank you. Yay! All
And
right.
you can use a static inside.
That kind of makes me feel better all of a sudden.
Yeah.
And you can use a static variable inside your lambda, but you can't access it from the outside. It's local to the scope of the function, but it's not a class static.
Correct. Thank you. Right, because you're defining the inline function call operator, right? Not the object itself.
But
Thank
it
you.
will get updated through multiple invocations.
Yes,
Like
because it's the same
one-
lambda object.
All right, so let's talk briefly at least about scope. It's actually not as hard as it looked to me, at least initially. Captured entity must be defined or captured in the immediate enclosing lambda expression or function. So if you just ignore this part of it at the moment, the enclosing lambda expression part, you already know all the other parts, right? You do this all the time. You use some variable as local because it's within, you know, the nested curly braces where you can use it. So nothing surprising there. It's trying to untangle what enclosing lambda expression might be, is the part that we'll probably just work on right now. All right, so all these things we should just expect to work, right? So I is assigned 8, j is assigned 2. We're capturing by value, default. And we go ahead and put out I divided by j. No problem at all because this was in the scope of things that we can normally do, right? We do this all the time. This is not surprising. All right, now we have a lambda function captured by value. Within the lambda, we have a j set to 2, and we have another lambda function that's capturing by value. Same thing, I divided by j. And then we're going to invoke m. And then out here, f. So when we do this, m, we would hope that we get 4. And when we invoke f, I'm sorry. Oh. When we have m, and here we're going to invoke m. We're going to then take this capture, this closure object, and it's being assigned to f. So when we invoke f, this is what we're going to do. Invoke m, we're going to get 8 divided by 2, we're going to get 4. So here what's occurred is this outer lambda expression is capturing by value, and the inner one is also capturing by value, and it's trying to access I. And it's able to do that because the enclosing lambda expression captured by value. And so it looks, do I have an I? I don't have an I, but he captured by value. Does he have an I? He has an I. So now I is captured.
So is it captured twice?
Well, I think this is a lot like you can only tell the speed of something or the position of something. Because the only way I would know was by trying to do something with I, and then for sure it's going to be captured. But I think, in essence, it's captured one time.
So maybe the challenge is what could happen if in the inner lambda we said mutable, you know? So
If we said
mutable.
Oh, mutable.
Yes. And we try to change the value of.
You'll see in a minute.
Could you clarify the rules as to like when you can leave off the return type?
Yes, and a few more slides.
Interestingly, this scenario, at least with references, it was captured by reference, Visual Studio 2010. IntelliSense claims that I is not defined, but the compiler is fine with it.
Yes.
It's just, it gets a bit tricky for IntelliSense.
I have a long list of things that IntelliSense doesn't like the compiler likes.
Yes. Yes.
George is somewhere. Is George in this session? Oh, the guy with the hand back there. You can go talk to him later. George and I had a long talk about IntelliSense and other things mismatching. He's our Microsoft taking notes guy. Look at that. Any other questions at this point? Okay. So we're going to do a couple more of these. So here we have a lambda that is capturing I. By value, obviously. Everything else is the same, and so this should behave the same because I was captured by the containing lambda expression. So let's not capture it. And we get exactly what we would want, an incredible compiler error that points exactly to the line where the error is, and it tells me exactly what's wrong. I is not captured. So I captured nothing. I is not captured. Make sense? All right. All right, let's have some more fun. We're going to capture by value in our outer expression, but we're going to capture by reference in our inner expression. And, of course, this is not going to do what you wanted it to, or you thought it might. We're going to get an error, which is assignment of read-only location I. because here I'm trying to actually modify that same thing that we did a couple slides ago, right? I captured by value, things const. So I can get wild with mutables again, and then I can do anything I want. So same thing, capture though this time and add mutables. So now I've captured I by value, but I is mutable. So we do something, and we now have modified I within our inner closure object when we execute it. And so I is some value, but we expect I to be unchanged, right, when we get out of here because we've captured by value. And sure enough, it does what we would hope it does.
Do you actually need the second mutable?
No, we don't. All right. We're having so much fun now, let's really mix it up. So we have I, j, and k, which are 1, 2, and 3. We're going to capture I in the outer expression by value. J and k we're going to capture by reference. And then within our inner, we're going to capture I this time by reference, j by value, and k by reference. And so what we're trying to figure out is, what's the association here, right? What are these things going to do? So value, reference inside, reference, value inside, reference, reference. And after I capture them, I'm just going to reassign them to 4, 5, and 6, make everything mutable so it stops complaining. Inside, we're going to print out I, j, and k. And then when we go ahead on the outside, we'll print out I, j, and k. So, we've captured I by value. And here, the value by reference. So we would expect it to be 4. J we've captured by reference. Here we've captured it by value. So what's going to happen now when we assign it? Right, we're changing the local copy, but it's not going to be reflected, of course, right, in our outer. And then k we've captured by reference, and then again by reference. And so we have the changes that we would expect to represent that from our inner and our outer. These are our sharp crowd. All right, so closure objects have implicitly declared copy constructor and a destructor. So, most of you know just what that means immediately, but it's always fun to demonstrate it. So there's this simple little thing, struct called trace, does nothing more than prints out whether we're constructing, copy constructing, destroying, or assigning. And we throw an I in there just so that we can use it later. So we construct our T, so we have an object, and we're capturing by value, and we're returning I divided by 2. I is a local, and we get construct and destroy because we've constructed and we've destroyed. So we construct T here and we destroy it when we leave our scope. But even though we've captured by value, we didn't use it in our statement, and so it's not there, right? Unless we use it, it doesn't actually get captured.
But in this case, you don't actually execute it. Intentionally.
But it's by value. And so, at the time of evaluation of the expression, the copy would have to be made.
The expression is never evaluated.
Oh, the expression is evaluated, and it's assigned to M. And I now have a closure object, M1. So I have a closure object, M1. This has been evaluated.
You might get a
I actually know it had to be evaluated because that's one of the rules where you can put lambda expressions.
You might get a warning that it's an unused variable. I don't know. Because you're not calling it.
I wanted one, but I didn't get one. Yeah, so because we don't use it, it's not captured. So let's go ahead and use it. Same type of thing. I'm assigning a local I to the traces I. This will be evaluated. The closure object is assigned to M1. And then for fun, let's go ahead and make a copy of M1 and assign it to an M2. All right, so T gets constructed. Copy construct. Yep, that's what I expected, right? I captured by value, and I'm using it. So T's got to get copy constructed. Make copy. Copy construct again at the assignment, which is really an initialization. And then we destroy all three as we leave the scope. Yes?
Pointy question, but what happens if you capture T explicitly but never use it? Instead of equal, you say T.
Why didn't you do that? Howard? If we captured T, but we didn't use T?
Chandler, if we capture T?
I strongly expect that will force a copy on the input. I think that the capture list is going to be interpreted explicitly, but I would need to spend a lot of time
So,
to be confident in that.
for some reason I have in the back of my head that's actually an error. But
That's easier to check.
a captured but not used, I think, is an error.
Quick to the compiler.
It was implemented dependent on the capture. People wasn't free to ignore that.
So here in a minute, you guys get to do something.
GCC does the
And
copy.
What?
GCC does the copy.
I'm so glad you have a compiler. If the rest of you would have brought compilers, we would have been better off.
It's not an error. It makes a copy. It does what you would expect with the function.
Okay.
Right? Like it's.
No, don't. That does what you expect doesn't always work.
Well, if it
fine.
were a functor object that,
Yeah, right.
that you're
Yeah.
passing into the constructor
Then
by
you pass it
value.
into the constructor.
Even if the constructor just drops it on the floor, you still pass it in by value to the constructor.
Okay. And so you are actually then getting a captured T or trace object within inside of the closure object.
That said, the copy might be elided in certain circumstances, but that would be rare, I think.
Well, if the copy has side effects, then you must copy.
Not always.
Okay.
Another hard question from over here.
What if you use RefRef
If you used ref,
R value reference.
Lambdas don't have
capture?
moves.
You can't capture.
I don't see how you can capture that.
Yeah, Lambdas don't have this yet.
Yeah.
Why is the closed object copied into M1 and not moved? You can't use the object afterward anyway.
Because that would have destroyed my example. Right, no, I just wanted to show that things copy around and then we have a bunch of them destroyed. We have a move example coming up.
So we are saying that just by capturing everything, it's going to make a copy of everything in its scope.
No.
Right?
If you use the default,
Yes.
it will only capture what's used, which is why in this previous example, we don't use T, so even though we capture default,
Yeah, because otherwise it will be disastrous. Like bigger
Oh, yeah.
you will have many answers standing around.
right, yeah, that would make Lambda unfortunately not useful.
Yes.
Oh, more questions? All right. All right, so Eric unfortunately left just as we're getting to return types. So this is the return type rule. If you omit a return type and the statement has a return such as return expression, then the return type will be whatever the expression would evaluate to after all the normal things, right? Same normal things as always. L value to R value conversions, array to pointer conversions, function to pointer conversions. So it just does exactly what you expect. I personally think, by the time we get to C++ 24, it'll look a lot like all these other loosely typed languages. I just don't have to type things in anymore. Okay, otherwise the type is void. Yeah.
I was under the impression that it was like the same rule as context where that you could only be one statement. You can have an arbitrary number of statements.
Yeah, so, I don't know where that came from.
Yeah.
It came from STL's blog post.
Oh.
It doesn't appear to be true. I couldn't find it.
I was under the exact same impression.
So was I.
Yes. It's very solidly. I'm really surprised right now.
I was too.
What if you have multiple returns?
Yeah.
Can you?
Do you get unification or something like that?
Multiple returns?
Well, I mean, multiple, like if you have an arbitrary if blah, 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 return this, then what if they're slightly different types?
Oh, can it then determine?
Exactly.
Well, I don't think it would then match this, would it?
Possibly.
You can.
It's a compiled error.
If you declare it as returning int and then you have multiple returns, it won't work either.
If you do that.
No, I mean, if you define the type explicitly and then return different types in different spots, it
Right.
will give you a
Then it does exactly what you expect, right? So any other function that you define returns, bar, and then as long as whatever you're returning can convert to a bar, it does exactly what you
If
expect.
it doesn't, it's
GCC 4.7 saying inconsistent types induced within return.
Yeah.
With the multiple returns of different types. Oh, good.
I have to agree with STL's blog post.
Okay.
The standard says that the compound statement of the lambda must consist solely of a return statement.
Okay.
If you omit the return type.
Can you tell me what section that is, please?
Are
you actually looking at the standard?
I'm actually looking
Okay.
at the standard.
The only reason I asked is because I looked for the same thing.
It's paragraph 4 of the lambda section. If the compound statement is of the form curly, attribute specifier sequence, return, expression, close curly.
Dot, return
No,
expression.
it's not a dot, dot, dot. It's an attribute specifier sequence that is optional.
Which is what? An attribute?
Those are not statements. Those are generalized attributes. So squares, like square bracket.
So that would indicate that none of this should work, right? But it does.
No,
So-
it's void otherwise.
Right. So
And most.
No, yeah, you had one just there with,
Yeah, so
with
so
two statements.
that
Here's
one,
one,
no,
for
that one
example.
should not compile.
It does.
I think
But
GCC is
you're
wrong.
saying it should not.
Yes.
I would have loved to try it on Clang, but my Clang doesn't. Well,
I will try this, but the standard doesn't seem ambiguous here. There may be a defect report. I haven't been following those for lambdas, but
Howard, do you know?
I don't know, and I haven't had to check the defect report on this right now.
Okay.
yeah.
All right. So I had also read STL's blog, of course. And so when all this stuff was suddenly working, I went and looked for.
I do agree with Chandler's interpretation of M3290. That's what I've got.
Thank you, 90.
Yeah, I don't see any basis for a compiler accepting your code.
I was in the previous session. The guy just kept saying, and he's on the standards body, just try it. I'm purposely not using names at the moment because it's being recorded, but.
in Clang, with first the setter and then return, I get warning. C++11 requires lambda with omitted result type to consist of a single return statement.
Yeah. A warning?
A warning.
Oh.
Not an error.
We probably implement this as an extension by default.
Okay.
I think so.
Okay, so don't do what I'm doing, and if it's more than one, follow STL's blog and just give it the return type.
Sorry.
It seems. Who wants to write portable code? Is that what you just said?
I'm checking on you.
Ryan gives me a warning, I'm fine.
Thanks. All right, we did this. We did this. You guys are fine. Oh, it was over there already. All right, so here's a move. Does anybody know this reference, or was it just me? I'm starting to worry.
It's appreciated.
It's pardon me, it's depreciated?
Yeah.
Yeah, it didn't have a very good shelf life, that's for sure. How many know this? All right, so those of you who know what this means, and if you want to go here and put in your name, you can get a shirt. Well, if you're, I'm going to give away the Lambda shirt like John has on. That has this code on it. To 5 people each day. So, you know, if you go there and just enter your name, you don't have to put your email in. If you put your email in, we're going to open source a JSON library and a YAML library coming up, as well as our distributed state machines are coming up. So the JSON and the Llama, the JSON and the YAML libraries are being released in the next month for open source, and we'll let you know. All right, well, the rest of you don't know what it means, don't want a shirt. Let's talk about story. So we've looked already, we've seen 2 different ways where we can have a type name of T, and we go ahead and make assignments. The other is we have auto, which is wonderful. If the Lambda expression has no capture, then it can be converted to a function pointer with the same signature. And since all of us love writing C-style function pointer type defs, I'm sure we'll be doing a lot of this. So, F-type, make the assignment, treat it like it's a function, and then call it. Lucky for us, that's not the only way to do it. And so we have std function now, which, how many of you use boost function? Like everybody? So it's like almost the same thing, except not. So it's a polymorphic wrapper, again, for things that look and act like functions, right? So we can take function pointers, member function pointers, functors, which would also then include closure objects. And it uses the declarator syntax. So R is the return type, and then we have the args that will be passed in. So R is the return type of that function signature, and then the args that would be passed in for the function. Just for those who don't remember what we used to do, all this ugly stuff now just looks the same all the time, which is brilliant. So, function pointers. Function pointers. I have a function, my agree function, takes a string, returns size. Here's my signature. I can just assign it, and then I can just call it. Member function pointers. Same type of thing. Here we have a struct. It has this method called size. I have a signature of, it's going to return an int, take no arguments. I'm going to use bind. So taking the address of the size method, I've constructed a my struct here called mine. I'm using it by ref, So I don't want to copy the thing in. I actually want a reference to this thing. So I use ref. And then now I can just call f as normal. Functors. So I have my functor, here's my functor, mine. Again, same signature for our function, our std function. And here I'm going to assign it by reference to f. Not going to make a copy. And then I'm just going to call f as if it's just some plain normal function. And then, of course, we can do the same thing with closure objects. So this will evaluate then to the closure object. It will be assigned to f. And then I can make the call. We're all good with function? All right, let's have fun with function then. So I have a function that takes an int, and it returns an int, and it's f1. I have another function, takes an int, returns an int, and I'm going to call that one f2, and I'm going to assign it the closure object after this lambda expression has been evaluated, which is going to capture by reference. It's going to take an integer as an argument. At this point, we learned what we should be doing is putting our return type here. I'm going to call up all my slides. We're going to go ahead and put I out to the standard output. If I is greater than 5, then we're going to take 2 steps back and call f1. Yes?
Isn't the compiler going to dislike that for not returning on one click that?
Yeah, we just learned that, but this compiler that I'm using, it doesn't care.
What I'm saying is that this is a more ordinary case of you don't always have a return statement at all.
You get a warning.
And you have no
Yes,
basis.
as well.
If you're looking at
If I is less than 5.
Oh, yeah. I'm sorry, yes. So I can just tell you that GCC is. No, I can. Wait. It calls. Yeah.
Is it a path?
Okay, you're right.
I don't know why. The typical thing when you don't return on a path is it's just an initial bit of data in the return. You don't use it in initials.
Right. We're not going to, but it would have been nice to be told.
I want to ask you, earlier you said there is like, if you're capturing if there's a function pointer, that only applies to a regular raw function pointer, not to these.
But these are objects. So we are using f1, the function object, right? We're using this thing, so it's going to get captured, and it's going to get captured by reference. Notice we haven't assigned it anything yet, but who cares, right? That's the whole fun about capturing things by reference. So now we're going to assign it something, and we're going to assign it, again, something that takes by reference. I'm sorry, captures by reference, takes an int, outputs whatever was passed, and it's only going to take 1 step forward and call f2. So 2 steps back, 1 step forward. You guys do this every day of the week except for this week, right? And then we're going to call it with 10, and we're going to end up with what we expect are, we're calling f1 with 10. So we're going to output 10. We're going to increment it and call f2. And then we're going to output that, the 11, decrement, down 2, and all the way down to 5. So a neat trick is we can go ahead and capture by reference a function that is just an object, right, that's going to store something useful later, and then utilize it. This was supposed to be the amazing Y Combinator version, but I gave up. So instead, we have a function that takes an int and returns an int, and we're just going to call that object back. We're going to assign it and capture fact by reference. It then going to compare, right, to is it 0, return 1, else return the value passed in times fact minus 1, which was a capture by reference of ourselves, but not yet, because this is the expression, remember, which will evaluate to a closure object that will then be assigned to the fact object, and voila, factorial of 4.
Now, could you just pause there for a couple of seconds?
I certainly can. Yeah, this is a great place for you to pause. I don't know why you'd want to do this in real life, but it's fun on a slide.
Just to torture test your optimizer and see if that can actually turn that in. It doesn't think good.
I was happy if the compiler gave me the right output, right? I mean, I don't know. Let's about that. All right, does everybody see what this is doing? So remember, this is nothing more than a type, right? So this is just an instance of that type, and we're capturing that by reference so we can use it. And when by the time we use it, it's now been assigned something cool, our closure object, as opposed to what it was when we first started evaluating it. When we first started evaluating it, it's nothing, right? If we could call it at this point, which we can't, we throw a nice exception. But so by the time we actually use it, it has something useful assigned to it. Because we call factorial all the time. All right. Now it's your turn, because you guys are supposed to bring compilers. Have till 4, is that correct?
Yes.
Okay, thank you. All right, ready, set, go. I want a class that can queue up callable things. Things is a technical term. The callable thing takes an int as an argument. The callable thing returns an int. The class itself is going to have a method that looks like this. Run, that's given an int as a parameter and returns some int. When run is called, each of the queued items will be called. The first queued item will be called with init as its initial state. The result then of that will be passed to the next item in the queue until there's nothing left, and then you return the final value. I see people typing. Return the final value. It's okay, we won't have to type if we don't want to. We've only got 10 minutes anyway. All right, so let's do that. Wait, does everybody understand what we're trying to achieve? All right, we'll just skip to the end. Wow, you guys did an amazing job. What's that? You're going to go? You're going to do it? Jeff's doing it. I'm sure. Others join Jeff. This is where you break out your compilers. Really? This guy down here, he's doing it. What's his name tag say? He might get a shirt just because. Dan, man, all right. The rest of you are doing it in your head, I know that. It's okay.
I actually did it while you were explaining it in my head, and I'm thinking about it, not necessarily the clever way to do it.
That is awesome. You can tell us in a moment.
I didn't come up with one that I said.
Okay. This is the worst part about showing code to this group, right? Oh, yeah, well, that's okay, but you know what you could have done?
No, Michael, the worst part is when you show code to them and they say, yeah, but that's wrong, you should do it this way. And
Yep.
you- And all you can say is, yeah.
I tried so hard too to get the return value of the lambda expression. It just hurts. Are you winning, Dan? Do you have a plan? That's okay. You file it in your head. I'm good with that.
There's
You have
a
an idea?
blackboard here.
Yeah, we can type on Blackboard. You got an idea of where you're going with it, Jeff?
Yeah.
All right.
Probably don't want it. It's not here.
Well.
So, we can kind of do a pseudo accumulate with this or something.
Yeah.
Use a stack instead of a queue, and we can compose functions.
You could. All right, so while the rest of them are working really hard, I'll show you, yes?
So, by the way, I consulted with another person who's actually on core, Richard Smith. There is a defect report about the Lambda return type.
Okay.
And it is essentially going to change the working draft to actually allow what the code you have to work.
Really?
Yes.
I almost feel vindicated, but it's for the wrong reason, so I don't know that I do.
The rules are, there's some interesting rules that are going to be introduced. So, for example, you will not be able to have a deduced return type if any of the return statements use an initializer list.
Okay.
But
that's already.
Yeah, I mean, it's kind of strange that that one doesn't work. But then all of the expressions and all of the return statements have to all, after decay, have the same type, and then that's the deduced return type.
Okay, so if they all have the same type after decay,
yes,
that's the return type.
Yes.
And if they differ, then clearly you.
If they differ, it's ill-formed. If there exists any return without an expression, then it's void, and all of the returns with expressions, the expressions have to have the type void.
All right, wonderful. Thank you.
It took a little bit of doing, but.
Isn't this essentially fold out?
So yes.
It just means it does what Doug wanted.
It does what Doug wanted.
Yeah, when you put the warning in, and the warning in, the standard says different.
All right, let's go ahead and move on. This now, I did it the same way in the sense that I actually wrote this, and then I tried as fast as I can just to write code. That's another way of saying this code's probably really bad, but I'm going to show it to you anyhow. So this is what I came up with. I called my struct machine, and my add is going to go ahead and take whatever's being added as a template type, and then I'm going to push it back. And we're going to come back here in just a second. I'm going to go ahead and push that back onto this vector, and the vector contains functions with a signature of returning an int and taking an int.
Since you're storing it in a function object anyway, why wouldn't you simply accept the function object as the parameter to add?
I'll answer that now. So this will allow it to convert, probably the other would too, but I like this because it works for my example. This then, type T, as long as it's compatible with this signature, will go ahead and work, right? So you get promotions. You're right, it is a case, but you know, this is a boostish type event, so we have to write the word template and type name, and yours didn't. But that happened to be my first one until I remembered where I was, and then I changed it, so that's pretty funny. If you're looking at the GitHub, you'll see the other version first. All right, and so then in run, and then run, I'm just going to use a for each, and I'm going to go through the vector, and it's taking then, of course, that function object. It's going to call the function object with the value that was passed in. I happened to do it this way, but there was no reason for it, right? I decided that I was going to capture V, in essence, by reference. So I make the assignment back to V, and I return V. So by the end, I'm going to get the final value of V returned back out of my run. It's going to go through whatever happens to be in that vector, all the different callable things that take ints and return ints, and the final result will get returned from run. So I made a foo free function here, just so we can have some more fun. We go ahead and add a closure object with this lambda expression. So we're going to multiply whatever I is by 3. We're going to go ahead and add foo. This foo thing just added 4. And then we have another where we're going to divide by 5. I run it passing 7. Does this make sense? So conversions happen the way you would expect conversions to. So this standard function, if the signature can be, if you can convert from the signature you have to that signature, everything's great.
So apparently you didn't use space between your two closing and brackets.
Apparently I don't, but I actually like it. Because visually when I look at that and I see the two, I know that's not everybody, but when I see the two stuck next to each other, I don't know. It looks like something else to me. I'm a white space guy.
And I know this is talk on lambda, but wouldn't a range 4 actually be?
Yeah, but this is a talk on lambda. It's much prettier. There were lots of other things too with initializers earlier too, but nobody brought it up.
Would you want to stood forward F? Does that make sense?
Where? I'm sorry.
If you could you have a move enabled version for the
Sure, you can have all kinds of fun things. All right, so let's talk about a few use cases for Lambda. We have just a few minutes left, which is great because I have to slice. First of all, so where can you use Lambdas? It's easier to talk about where you can't use Lambdas. Lambda expressions have to be somewhere where they're evaluated. So they cannot appear in an unevaluated operand. And I love the standard. An unevaluated operand is something that does not get evaluated. It's neat. So these, as far as I know, these are the ones that are unevaluated operands. Mr. Smarty in the back can maybe help me here. But as far as I know, this is it. They can't appear with type ID, size of, no accept, and decal type. Beyond that, you can stick them anywhere you want. All right. This is what I think you should do. So this guy, you know, Stepanov is a sad man. He loves algorithms, and algorithms are awesome. And then what do we end up doing is, or at least most of my clients end up using all the containers and never ever look at the algorithm. There's 4 each. Yeah. And then there's all these other really cool algorithms that do stuff, right? And so earlier, I was glad Jeff threw up that slides, multiple slides of all of these algorithms. And for myself, part of the reason that I don't use a lot of them is because they often require setup somewhere that will eventually get passed in, but it's so far away from the code that I want to use that it just, at the end of the day, people are hunting around trying to figure out what you're doing. And so I think that's a turnoff for a lot of people in using them. But you don't have that excuse anymore, right? So you're gonna have to come up with a new one. So just go through and revisit all of the standard algorithms and look, which of these would work great with lambdas? That's like homework assignment. All right, so standard algorithms, callbacks would be a great place that you could use them. Runtime policies, right? Somewhere we kind of did that with the am I done yet or not? Places where you pass stuff in at runtime to make conditions and make changes and decisions about what you're doing. locality, obviously, of expression. I wrote this one down while I was on the plane, and then after I wrote the slide, you'll see why. It's a really crummy idea. It's like bind, but not. So here's my bind example. All right, so here's this thing. It's a free function called bar. Takes a string and an int, and it returns the int and the size of whatever the string is. Profit item, socks, of course. Foo, if we wanted to call foo, which takes something or another, and a moneymaker, though I didn't put it up here, is expecting an int. What I would have to do is bind this somehow so that I can get called with the int. So I bind in the profit item and then a placeholder, right, for when I call it. And then eventually here, I'm going to call f, which is going to be this bound functor that takes a single argument, the placeholder. And we end up with this thing, right? 8 times the size of socks is my profit. But I could have done this instead, right? I'd capture profit item by value. I'm going to have a signature where it takes an int, and I'm going to return, let's just call it bar profit item m. A lot of people I work with can't read this, and I'm pretty certain some of them will be able to read this, so this would be cool. Except that you can't do currying, and so then all kinds of bad ideas start popping up. So then this is where I decided that instead, I want to know how you guys are going to use lambdas. What do you think? While you're thinking, I'll tell you another thing. Initially, I thought my main use of lambdas would be just small little functions that I use for bits and pieces and whatever. And I don't actually know what it was. Something as I was reading through the standard made me think, you know, I use other languages that have lambdas, right? Unnamed functions. How many of you use JavaScript? Oh. Not very many. All right, well, whatever.
I have, but
if you were to do that in JavaScript, then you don't write like little one-line lambda things. You write like pages of stuff that eventually becomes some lambda function that gets passed around. And just like unnamed functions are all over the place. Why? Because that's the way the language partially started off, right? And you just get used to doing it. And so now we have this powerful thing. Who knows? I've heard a couple people say that, you know, that I expect these only to be small little snippets of stuff. They may not be small, but no. I personally don't know.
So you're gonna have a
How are you going to use them, Jeff?
C++ environment in your web browser, so you don't need JavaScript?
That would be so cool.
That would be cool.
Use them, right.
Okay.
I can see that algorithms would be sort of foremost use case. I mean, having to put a loop button somewhere else just doesn't really make sense. But the question I have is, why can't you? Why isn't your second? Why isn't your lambda-based example of the bar?
Well, okay, so certainly current you can't do, right? So I don't have the ability to have placeholders, and I can't call this with 5 values when I really only want 1. The signature says it's going to take an int. I can't just call it with 5 ints. Bind is great, right? I get this object back. The signature was it's going to take an int, this previous thing, right? When I call this, if I want to pass it 20 ints, whatever. If I want to pass it whatever, it just doesn't matter, right? As long as placeholder 1 matches what I need. That's awesome. Now bind's crazy powerful.
But when you say you can't do currying, are you saying your second call to work or just the control laws?
I'm saying that I can't have, I can't call it with a different amount of arguments than the signature that's set up as. I should have used maybe a different. No, I can't do. Good. What do you mean by that?
No, yeah, just NPM, comma, NPM equals 1.
Down here? Oh, no, you just, because you
Not
have the
there,
body
but
there.
if you are declaring like an auto and then reusing. If you are to declare a lambda outside and reusing it multiple times.
Right. No. Fairly certain that's not allowed. Default values on parameters not allowed. All right, well, this is officially the end of the Lambda session. Are there any following questions or follow-up questions? Yeah.
Why would you
Pardon me?
Why would you use Lambda?
Yeah, so some of the things, for example, for each, right? It's so much easier in our first example to iterate over a container using for each. Everything's right there, and you're going to perform some tasks on everything there. And you can just write it as a lambda, so it's local. Otherwise, something has to get called to operate on each element within the container, and so you'd have to define that somewhere else, not where you're using it. And so the locality is a big issue, especially for maintenance. But unnamed function objects, just like we use function objects all the time, but now we can define them right in line.
So it's a reusability?
My understanding is now, this is just from reading, it might have been STLs, that lambdas will perform better than the same exact function object you might have defined above as a structure.
But what about, I'm interested about that same question. You started by defining a while loop, you remember?
Yeah.
Without returning to functions. Is a lambda going to perform better than the original loop you have when you started by assigning, the first iterator, the beginning
Yes,
iterator?
yeah. The for each is just going to perform better.
Okay.
Yes.
And what about the primitive while, and can you go back to the first?
I can. If you guys want to go there, the slides are there. By the way.
You have, you started by assigning, the begin iterator, and you were iterating while the iterator was not the end one. So I guess that was the first slides.
Oh, that was, way back there.
There.
Yes.
So is a lambda going to perform better than the body of that while?
Yes. And the reason I say this is because for each with a functor performs better than this.
Okay.
Somebody who's real smart here and about why the compiler can optimize that better can tell you why. I don't know.
Can you repeat the question?
Why, for example, the lambda version, why the lambda version with for each performs better than the while loop?
I don't believe that's true.
You don't?
No. I'm happy to argue about optimizations, but I don't believe that it's actually true. The only reason it might be true is if you have a loop, you may have dependents within the loop that the compiler can't prove don't exist. So one thing that lambdas and the for each sometimes help with is proving that in fact the iteration, like the trip count of the loop,
right,
doesn't depend on the operations within the loop.
Right.
But that doesn't always pan out, and compilers are really good at proving this for normal loops. I wouldn't expect them to perform differently. I would consider it a bug if they did.
Right, so the smart guy with the compilers in the back says smart real compilers that you should be using on a daily basis should do that.
Mind you, I can only really speak for LLVM here and Clang, but I would be shocked if LLVM and Clang compiled this loop into slower code than any code involving a lambda, and we actually might do a worse job with the lambda.
A worse job with the lambda?
Yeah.
So to summarize, Chandler, you said the lambda version of this code will perform better than the primitive while. Or
No.
The other way around.
I'm saying that given this exact code, right, I would not expect there to be any difference in theory. In practice, lambdas are newer, and we have less experience optimizing them, so we may have missing optimizations with lambdas.
Okay.
Like, if you take the limit over time, as we learn all of those tricks, I would expect the two to produce identical code.
So it's just a matter of time that someday we may discover a way, or is the fact that here you are not calling any function?
You're not calling any external functions, you're not writing to memory, which might alias some other memory. There's never going to be a problem analyzing this loop. The best you're ever going to get is a lambda to equal that loop's performance.
Okay.
Thank you. Yeah.
We've got these behavioral libraries, Phoenix and Lambda and Boost. I was wondering, with the introduction of this into the standard, where do you see, has the role of those libraries changed?
I just give you my personal opinion, right? And Joel de Guzman and I talk a lot. So first of all, Phoenix should be replacing Lambda anyhow, right? So if you're using Lambda still, you just shouldn't. Boost Lambda, you should already be on Phoenix. The advantage I see when I need it of Boost Phoenix is it's polymorphic, which we saw early on in one of these slides. This one in particular. This Phoenix function of total elements multiply equal some placeholder doesn't care about the type. It will determine the type when I call it and use it. And I can't do that with a lambda, right? I actually have to say it has this type of parameter for the inputs and the outputs, and yeah.
What's Chandler's take on performance with this one? Oh, he's gone.
Left. He's smart.
I find that in real life, and this is why I'm really excited about Lambdas, is that I never have something that's
sure.
I've got accessing members of classes that require more complicated bind and call functions, another bind, and I just get buried in these binds and things, and I forget to call ref once, and everything just blows up. And so lambdas are just so exciting because it just makes these things, I can write it the way it's supposed to be.
Right, I completely agree. And then if you do it wrong with the current libraries that we have, I mean, it's just more of what the output is a disaster.
Maybe I can say that when we deal with parallelism on different kind of strategy to partition data and use traffic card, and like expression are very useful so that users focus on their codes, and we can provide them different way of parallelize the data and cause the data with different kind of distribution.
Right.
So we have different kind of for each with different strategy. But we can have lambda function very complicated, but we just focus on what to do on each data.
Right.
And we don't focus on the for each, which can be different regarding the hardware or the way you want to parallelize data.
Right.
So
great. Thank you. That's a great example of parallelism where that loop is magic. And something's going to happen, right?
We don't care about the loop. We just want
just what is the thing I'm trying to perform. Good point.
And we can have lambda function, very complicated, big lambda function. But people just see it as a function, a real complicated function we need. But they know that this function is applied on each data of the collection. And the way it's parallelized, okay.
All right, so we're now over, and I can't get internet here on my laptop, but I can get on the tablet. So the names that came up, top 5 were Marshall, James McNellis, thank you, Andy Weber, Kyle NY something. Better than butchering it, right? Pat Knotts. So if you're one of those people, if you want to come up, I have like 3 sizes and I'll give you a shirt. You can get your very own Lambda too.